Welcome to lecture number 9 of module 3. In this lecture I'll discuss about the SBC, which is a reactive power control device, and also it can improve the dynamic performance of the power system. In the next module, that is module number 4, the facts, that is a flexible AC transmission system, is mentioned, but the fact SBC is mentioned here, and this SBC is a device of facts family. So here we can now see what is the facts, that is a flexible AC transmission system, what are the definitions given by different organizations, and what are the various devices and how we can classify them. Then I'll go on the static var compensator, that is a SVC, and also we'll see the comparison between the STATCOM, that is a static synchronous compensator, and SVC. So to begin with, here the flexible AC transmission system, that is known as the FACTS, and are the name given to the application of power electronics devices to control the power flows and other quantities in power system. There is always question that whether which device is FACTS device or not. So the term which is used here, the power electronics devices. For example, if you are using a simple capacitor here with a mechanical switch, this is not a FACTS device. But if you are using some here thyristor switch, some switching mechanism here you are using based on the power electronic devices, then this device is known as FACTS device. Then it is called thyristor switched capacitor, that is a TCSC. So for it should be a FACTS, there should be a power electronics device or apparatus, and it should be operated very efficiently and very quick time. So that's why the FACTS, that is a flexible AC transmission systems, are the name given to the application of power electronic devices to control the power flows, that is maybe real and reactive, and other quantities in the power system. Other quantities are voltage, we can change the current, we can control the reactance, we can control the phase angle. So these are the various power system quantities. As per IEEE definition, to add any confusion, IEEE gave a definition that the FACTS, the AC transmission system incorporating the power electronic based and other static controller to enhance the controllability and increase power transfer capability. Means we can enhance the controllability, means we can control some of the power system quantities. It may be your voltage, it may be your reactive power, it may be your real and reactive power flows in the transmission line, or vice versa, and also that it can increase the power transfer capability of the system. By that, why we are controlling this? Why we want to control all this quantity? To enhance the power transfer capability or to improve the performance, that is a static as well as the dynamic performances of the power system. The flexibility of electric power transmission is defined as the ability to accommodate the changes in the transmission system or operating conditions while maintaining the sufficient steady state and the transient margin. Means the flexibility here is related to that how much margin, that is a steady state margin as well as the transient margin. Whenever there is a severe disturbance, the system goes in the transient region, and then how much margin do you have that you can operate your system efficiently. The FACTS controller, that a power electronics based system and other static equipment that provide control of one or more of the AC transmission system parameters, and the parameters are normally the voltage, angle, and X of the transmission line. With the help of these three, we can control other, that is the real and reactive power flows in the transmission line, and also we can, the reactive power control at any bus can be changed accordingly. Now the question, why we are going for all these FACTS devices? Let us go back. What are the limitations of your transmission system? First and the major limitation, normally it is called the system stability, because we know that we cannot transmit the maximum power without losing the stability, because all the lines are having some stability limits and we have to operate well below that limit. So the system stability limits again can be categorized. You know it very well. That is your transient stability here, the voltage stability if you are governing here, the voltage. Here we are talking about the angle. Sometimes it is also called angle stability. The dynamic stability is also a part of your this angle stability. Here the steady state stability, the frequency collapse where we are talking about the frequency stability, and it may be your subsynchronous resonance problems. So AC transmission system is limited by the stability limits. As I mentioned, the various the stability limits are there, and then we have to improve. If you want to enhance the power system performance, you have to improve these stability limits, and thereby you can transfer more power, as well as you can control your power system for the given objective. Another limitation of AC power system is the loop flow. Loop flow is nothing but the flow. Suppose a system here, you are having a generator here, this is having a line here, here again we are having another line, and finally we are having another load here, and now we can say the power which is flowing here is coming from here rather than here. So the power which is going all the way from here to here and finally coming here, that is called your loop flow, and it is nothing but it is due to the impedance seen by the current. We know the current flows in the AC network, and it depends upon the impedance seen by that current, and so always the current follows the minimum impedance path. So here we don't know what is the problem with the loop flow. The major problem with the loop flow is that it will increase the system losses. Now you can remember here it is I, and then it is I square R. Again it is going to be added, so it's the more loss. So to avoid that, we have to control somewhere, that you can use some devices that can control, and then in fact device is one of the option. Another is your voltage limit. We know that we cannot operate our power system satisfactorily beyond certain limit. Normally, just we say for EHV line, the plus minus 5% is the limit. However, for this other, it may be plus minus 10% limit, and beyond that, we may face several problems. Suppose the voltage is more, there will be a lot of flashover on the insulators, flashover insulation breakdown, etc. So that will cause another problem. If it is under voltage, then there will be huge reactive power generation of the induction machine loads, etc., and that will again require more reactive power. So we have to stick in a certain band. Thermal limit of the line. We know this limit. The lines of the lines are limited by the thermal limit. Means we cannot flow the power in a particular line beyond its thermal limit, because if thermal limits is the limit, if you exceed that power in that line, beyond that limit, the line will sag, and there will be another problem. What will happen? Normally, if your current exceed here, this is your normal catenary, that is form of a transmission line. If the temperature of this wire increases, there is a possibility that it will be again more sagging, and then here there is a possibility here that we may lose the ground clearance, and there may be flashover, there may be danger of the life, and so many problems will occur. And again, if the current will increase, load will increase, there will be that this line will melt and this will be broken, because tensile will be less. So that is the extreme case, but even though there is a small increase in the temperature, only this sagging will be more, and the flashover and the other problem will occur in the transmission line. So we have to do in such a way that we can utilize those lines. They are not hitting the thermal limit. We can transfer the power from one line to another line, and then we can achieve the performance of more power transfer over the corridor or subset of networks. Another problem is your high short circuit limits. We know that if you keep on adding the several transmission lines, let's suppose at this bus we have the several lines going and coming. In this bus here we are having the circuit breakers in each line. Now the rating of these circuit breakers are decided by the fault level, that is a three-phase fault at this bus, and that is decided. Now if you are connecting more line here again, let's suppose, what will happen? The fault level of this bus will increase, because we are adding another parallel path here. This earlier 3 parallel, now 4 parallel. So impedance will be reduced and the fault level will be increased. And there will be possibility that we have to replace these circuit breaker ratings as well. Means we have to go for higher current rating circuit breakers, and again the cost will be more. So once you are keep on connecting AC network, the high short circuit current is going to increase, and that will one time it will limit that we cannot get the circuit breakers of that rating, because we have some standard practice of the circuit breaker ratings like 63 MVA, maybe it is 80 MVA. So we know this what is the current limit and what is the power limits of this, and based on that we decide it. So these are the various limitations. Already other limitations that you know, different effect and more corona loss, etc. So those are the minor problems in the AC transmission system. So to avoid this, the FACS controller can do much in these directions. They can, no doubt, here the FACS devices will not alleviate these problems completely, but they will improve the performance of the system. For example, the transient stability, or you can say stability of the system. Using the FACS controller, we can improve the stability of the system. Means we can have the more margin, and then we can operate our power system satisfactorily. So it can, stability we cannot say that there is no stability problem, but we can say we are enhancing the stability limit by using some extra devices, and that is FACS that we are talking. We can avoid the loop flow, we can go for the voltage control as well, we can load the line up to thermal limit, and we can reduce the short circuit limits of the buses, etc. Now let us see what are the various advantages, means benefits of the FACS technology. There are basically the two major advantages of the FACS technology, FACS devices, or you can say FACS controllers, to increase the power transfer capability of transmission network. Means it will increase the power transfer capability of transmission network, and it will provide the direct control of power flow over designated transmission routes. It is not necessary that wherever you are putting that device, it will control power flow or power system quantity of that line only. It can control the quantity of other line, other designated route or other designated corridors. It can control, and therefore what will happen? We can improve the power system performance accordingly. So with the help of these two very major benefits, means that will increase the power transfer capability of the network, and it will provide the direct control, means you can control the power flow over the any designated route. Based on that, we can have the various opportunities, and those opportunities can be again written as first one, that it can control the power flow as ordered so that it follows on the prescribed transmission corridors. Means we can control the power in the some lines that it will meet the requirement of the specified power flow in certain corridors, means set of the lines, maybe one line, two lines, and so on. So in the transmission corridor, we can fix the amount of power. Another is here the use of control of the power flow may be to follow the contract, meet the utility's own need, ensure optimum power flow, right through emergency condition, or a combination thereof. So use of control of power flow may do several objectives. For example, I can tell you, let's suppose we have here one utility and another here consumer is here in this utility. This is a consumer, here one generator in this utility, and we want the power, and then here from this transmission line we want the power here. So the power which is the agreement between these two can be controlled, that how much power they are having in this line. We know, suppose your generators are here, one generator, the two buses are here. Now here another your load is there, and let's suppose here we have another generator and the load. It is not necessary that the power which is taken by this generator is directly coming here. It may be we cannot identify the power flow because the electrons are not having any color. So the current here which is flowing, that is basically in which line, what is the contribution of these powers or the contribution of this load can be obtained, and normally this is known as the power tracing. So we can do the power tracing, and then we can see that which is contributing how much. So here the use of control of power flow may follow a contract, means we can meet that exact contract what is over that line. Means we are having a line, and then we are having contract that will flow 100 megawatt power over that line. So we can meet that requirement by controlling the FACTS controller. So it can meet the utility needs, and it will ensure the optimal power flow. Means we can optimally flow the power so that we can achieve our objectives, maybe your minimum cost, minimum loss, or other objective that we can achieve with these FACTS controller. In emergency condition, suppose one line trips, what will happen? Other lines may be overloaded. So in that event too, it may elevate that emergency condition by rerouting the power flow in other lines. Third is your increasing the loading capability of lines to their thermal capability, including short term and the seasonal. Means here we can increase the lines loading to their thermal limits by controlling the FACTS controller parameters. What will happen? Means we can, in the short term as well as in the seasonal, means for long term, we can control, and then we can load the lines up to their thermal limits. Increase the system security through raising the transient stability limit, limiting short circuit currents and overloads, managing the cascade blackouts, and damping electromechanical oscillations of the power systems and the machines. By controlling, we'll see later on, even though using SBC, we can see we can damp out the oscillations. We can improve the transient stability of the system. We can limit the short circuit currents, and we can manage the cascade tripping as well. What happens? Normally, I'll tell you one example. Let's suppose here this is a line, the load is here, and this system is running smoothly. If this line is tripped, what will happen? This complete power will be followed through this, and there may be possibility this line will be getting overloaded. There will be some protection system, that is your overcurrent protection or distance protection. What will happen? This will be also tripped, and there will be cascade tripping, and whole system will be in the blackout. So with the help of controlling, if there are other lines, we can control easily, and then we can control the blackouts. Means we can avoid the blackouts in the system. The FACTS controllers can also provide the secure tie line connections to the neighboring utilities and the regions, thereby decreasing overall generation reserves requirement on both sides. Again, I have explained in the previous lectures that connecting two tie lines, means connecting two systems with a tie line, can reduce the reserve margins, and then we can have sometimes very secure tie line can provide the emergency support of one area from the another area. So it can do very good duty during the emergency event. And of course, it will decrease your generation reserves, and therefore we can run the power system at higher PLF. It also allows the secure loading of the transmission lines to a level closer to the thermal limit while avoiding overloading, and reduce the generation margin by having the ability to transfer more power between the control areas. Means we can again go up to the secure loading, means we can go up to its limiting value, and then this will again improve the power transfer capability between the two areas. Another opportunity that we can achieve with the help of FACTS controller, that it can damp out the power system oscillations. Why the power system oscillations? In the power system, there are various type of faults, and that faults here, for example, if you are having a generator, let's suppose single machine infinite bus, here we are having two lines, this is your infinite bus. If there is one fault in the transmission line, what will happen? This machine will accelerate and decelerate, so there will be some oscillations in the rotor angle delta and also the speed. So this machine will keep on oscillating and then it will be going at the certain value. So this oscillations can be dumped out quickly with the help of the power system FACTS controllers. It can again prevent the cascade outages by limiting the impact of fault and the equipment failures. It provides greater flexibility in setting new generation. What does it mean? I want to say that here, let's suppose in the power system, now these lines are loaded. There is a possibility we have another line here that is underloaded. So we can put even the generator here, and then by putting some device here, we can control the power over this line, and then we can put here or we can put anywhere, and then we can utilize the properly. So FACTS controller may allow the proper setting of the generators with the help of controlling the power flow in the lines. Another is upgrading of the lines. Means at the same time you can go for the upgrading of the lines, means from one conductor to you can go for the other size of conductors, and then you can load up to that limit by using the FACTS controller. It also reduces the reactive power flows, thus allowing the line to carry more reactive power. So it can reduce the reactive power in the transmission line so that we can go for the more active power. What does happen? You can see this, you are having a transmission line here between the two buses. Here this current which is flowing here, that is magnitude, and here this is I square R loss is there. So this line has some limitations, that I, that is a real and reactive components are here, means I is nothing but your IR plus JI. Here you can say real part and Q part. Now if you are going for this is less, then you can go for more real power current, and then you can transfer more real power than active power. So if you are having this, then this will be reduced, because this I square R, I square is the limiting value of the transmission line, because I square R is the loss, and then it is, you can say, limiting value, that thermal limit. So with the help of, if you can control this, we can minimize this, we can go for more real power. Again I said it can reduce the loop flows. Again we can control the power, thus we can redirect the power in the different fashion according to our requirement. So loop flows can be reduced. It will increase the utilization of the least cost generation, means we can have the different generating stations, and then we can go for the economic dispatch. For example, you are having several generators here, then you can run this economic dispatch without any problem. Normally what happens? Here there are some possibilities, some transmission lines are getting congested, then we have to reduce the loading of the cheap generator sometimes. But with help of here FACTS controller, we can redirect, and then we can load, we can utilize the cheap generation first, followed by the next expensive generator. So the economic dispatch here, that is a optimal power flow or economic generation least cost operation, can be achieved very efficiently compared to the without FACTS controller. So these are the major advantages of the FACTS controller. Now, remember in the very beginning, I discussed about the FACTS, HVDC. And again, in the next module, I will discuss about the salient features of HVDC control. Now, always the question arises that whether we are going for HVDC system or FACTS controller, because the HVDC system, here we are talking the transmission is the DC. We are generating AC, utilizing AC, but the intermediate part we are transferring the power over the DC lines. So here both are using the power electronics devices. In HVDC also we use the converters, we will see in the next lecture, next module of the lectures, and the FACTS controllers also use power electronics devices. So these two, FACTS as well as HVDC, are the complementary technologies. The role of HVDC is to interconnect AC systems where a reliable AC interconnection would be too expensive. Or if you want to transmit power over a long distance, more than 600-700 kilometers, AC is not practically feasible and it is very expensive, because you have to go for the several stages of compensation. So you can use the DC system, and already in India, in UP itself, we are having HVDC, long HVDC line that is coming from the Rihand and it is going to Dadri near Delhi. And this line length is approximately 900 kilometers, and we are flowing 1500 megawatt in steady state condition, and the voltage is operating plus minus 500 volts, means it is a bipolar operation. Again, I will discuss HVDC in the next module. So, the advantage of HVDC, that's the independent frequency and the voltage means control, means here the two independent frequency system can be connected and the power can be controlled independently of the system frequency of the two areas. We require only two wires maximum, or one wire. We can use the ground as a return. So the lower line cost, of course, than the three-phase system. It is the power control is possible, voltage control we can do very well, and stability control is also possible. However, in the DC there is no stability concern at all because P delta angle is not existing there. For the FACTS, the large market potential for the FACTS is within the AC system itself and on value added basis, where means FACTS technology is incorporated in the AC system itself. If you are having AC transmission system, if you are going for the DC, then you have to build a new transmission line, the DC, and you have to put the converters, etc. But here what we are doing, we are not going to change the transmission line, we are not going to change anything else, only we are putting some devices in the AC system itself. And what should be the basis that existing steady state phase angle between the buses should be reasonable. Why it is so? Because we know that this value is, this is your delta, this is P, I am talking this curve from very beginning. Now if you are loading the power system here, your delta is this much. This delta is the angle difference between the two buses. Now you have the margin up to this one, this is your P max. So if you are already operating here, whatever the device you are using, you are very close to P max and the margin is very less with you. So the point it is noted here, it means if you are having the more margin, if your delta difference is less, then you can load more, means from here you can go up to this margin and this is very high. So this is a value added addition. So the existing steady state phase angle between the bus nodes, that is two ends, should be reasonable, should be small. The cost of FACTS solution is lower than HVDC cost, of course. We will see the cost of FACTS devices are always lower than the HVDC cost. And the required FACTS controller capacity is lesser than the transmission rating, because the transmission rating is this much. So it is always this rating is less than capacity of the transmission line. So these are the 3 points where we have to decide. Now if you go for the comparison for HVDC 2 terminal, the cost for the 200 megawatt throughput, means that is the power which is we are going to transfer, here it will require this $40 to $50 million. However, the FACTS is a $5 to $10 million. So you can see this is almost 8 to 10 times lesser compared to your HVDC. So this device is cheaper, economical as well. Now the FACTS technology is concerned with the development of following 2 areas. Now, why this FACTS technology is so much becoming popular and popular? The reason behind that, the high rating power electronic switching devices and the pulse width modulated converters are existing. Means earlier the line commutated converters, the thyristors were there and they were creating a lot of problems. But now we can use the pulse width modulations for the converter circuits, and then we can maintain even the power factor unity. And also we are right now we are having the power electronics devices with the more voltage as well as the current ratings, and that is making feasible, and also the cost is reducing. Another reason, that is the control methods using the digital signal processing, that is called DSP, and the microprocessor and microcontrollers are feasible nowadays, and based on that we can control very efficiently and smoothly. Various devices, normally in the power electronics, we know it very well, simple thyristors. We have the IGBTs, that is it is a transistor based technology, that is a insulated gate bipolar transistors. We are having GTOs, gate turn off thyristors, MCTs, that is the metal oxide thyristors, MOS control transistors. So you will see what is the comparison. of the power semiconductor devices. I have just compared the thyristors, GTOs, IGBTs, SI, that is the static induction thyristors. Here MCT, and we are having the MOSFETs, that is a MOS field effect transistors. Presently we are having approximately 8 kV voltage rating and 4 kiloampere current rating of single unit of thyristor. Whereas the GTUs we are having 6 kV and 6 kiloampere. IGBTs of course we are having 1.7 kV and 0.8 kiloampere currents, and others are also the lesser than your thyristor and the GTUs. The other difference between these all 6 power semiconductor devices are voltage blocking. That is, here it is a symmetrical and asymmetrical is possible. Here symmetrical and asymmetrical both are possible. Here only asymmetrical, asymmetrical, here symmetrical and asymmetrical. Means gating here we give the pulse in the thyristors, GTU we give the current, IGBT we give the voltage, and SI we give the current and the voltage, and so on and so forth. If you see the voltage drop, the thyristors are having the minimum drop, that is 1.2, however your GTUs are 2.5. Switching frequency you can say here it is 1 kilohertz, here the GTUs are 5, IGBT is even to 20 kilohertz. Now the targeted value, it is expected in the future we can achieve the thyristors of rating 10 kilovolt, and here we can get the 8 kiloampere. We are also expecting the GTUs, they will be available here in the 10 kilovolt rating of single unit, and here 8 kiloampere. Similarly, the IGBTs also we are expecting more development, and then again the cost also it may keep on reducing. So the two versions of switching converters in the power applications, that is the FACTS controllers, we can categorize the devices into two categories. One, they are using the converters, so it is called converter based FACTS controller, and others are simple without the converter FACTS controllers. So the two versions of switching converters are feasible depending on whether the DC storage device utilized is. Means if you are talking about the converter based technology, so if you are using the power storage device as an inductor, then it is called current source converter. If you are using capacitor, then it is called voltage source converters. HVDC basically use the current source, however this VSC is used in the STATCOM and other active power filters. The comparison, if you want to see that CSC and the VSC, in the current source converters, inductor is used in DC side, however in the voltage source converter, capacitors are used. In the CSC, the constant current is achieved, however in the voltage source converters, constant voltage is achieved. The CSCs are having more losses, whereas this VSC is less losses and so more efficient. CSC we can have the fast control and accurate as well, however this VSC is slow control. CSC requires larger and the more expensive, area required more and it is more expensive, however the VSCs are smaller in size and they are less expensive. The CSC, that is a current source converters, more fault tolerant and more reliable. However, the VSC, they are less fault tolerant and the less reliable. In CSC, the control is very simple. However, the VSC control is very complex. CSC not easily expandable in series. However, the VSC that we can easily go further, keep on adding the parallel to increase the rating. Now let us come to the various devices and how we can categorize. So the types of FACTS controllers. Now we can categorize. First category I made based on the converter or non-converter. Now here again we are going for the different, means how they are connected in the system, and then we can classify the FACTS controllers. First one is your this series controllers, means they are connected in the series as its name. Shunt controllers, they are connected to the bus. Combined series controllers means they are placed in the series of the two lines. Combined shunt and series controllers means there will be a shunt is always connected to the bus and then to the ground, and then the series inside the line. So the series controllers, it could be a variable impedance such as capacitor, reactor, etc., or power electronics based variable source of main frequency, subsynchronous or harmonic frequency. You can see here first, this is, let's suppose, a notation of FACTS controller. Then what I am going to do here, just I am putting here in the series of this line. This is line, we have put this FACTS controller. Then it is called your series FACTS controller. If you are putting in the shunt, here you can say it is a shunted at the bus or in the line's end. Here it is called shunt FACTS controller. Now if you are using the series here and series here, and again if you are connecting with the DC link, then it is called your series and series FACTS controller. There is a possibility you can have one shunt and then one series, and then we can have the coordinated control. Then it is your shunt and series FACTS controller, and this is a coordinated, because here the controls are we are coordinating in such a fashion they can operate smoothly. Another is your, here it is also shunt and series FACTS controller, because one shunt, here is series, but they are connected with the DC here power link, and it is, that's why it is called the unified. Here there is no control, it is a unified control, automatically it is taken care of, and then it is called unified series shunt controller. Here it is called coordinated control shunt series FACTS controller. So in series controllers, I can say here it could be a variable impedance, means as I put here in the transmission line, what is this? It can be a variable X, or it can be XRL, whatever you can say, and or it can be a voltage source, means it can be simply XL, it can be your XC, it can be a voltage source, and this voltage source may be of the same frequency component of the operating system, or it may be sub-frequency or super frequency, or the combination of all these is possible in series controllers. All series controllers inject voltage in series line. No doubt these controllers will inject voltage, whatever the current will be flowing here. If it is a Vs, of course it is injecting. If it is a XL or XC, some I into XC is injected. So all the series controllers injects voltage in series with the line. If voltage is in the phase with the coordinator, if this voltage which is injected is in phase coordinator of this VI, phase with the line current here, which is flowing line current, if it is in the coordinator, then it only supplies or absorbs the reactive power, and then it is working as a variable reactive power source. For other phase relationship, the real power is also controlled, and then it is called your series controller. Now let us see this other controller, that is your shunt controller. It could be again the variable impedance, as I said, means impedance here X. It may be a variable source or combination of these. So this is your shunt controller. All shunt controllers inject current into the system at the point of interconnection, as true. Here this is connected here with this FACTS device. This will inject the current, again it may be leading or lagging current. It will inject into the system where it is connected. If injected current is in phase quadrature with the line current, here this line I and this is your I injected, if they are in the quadrature, then it only supplies or absorbs the reactive power. For other possible relations, here the real power will be also controlled. In the combined this series and series controllers, it could be a combination of separate series controllers as coordinated or unified. Already I showed you. Controllers provide independent series reactive power compensation, means they can control the independent reactive power as well controlled. The real power transfer capability of unified series controller, known as interline power flow controller, makes it possible to control both real and reactive power flows. Means we can change the power from one line to another line, and this interline power flow, that is called IPFC, means IPFC is one device that is an interline power flow controller, that is an example of series controllers. Unified means the DC terminal of controller converters are connected together for the real power exchange. So here this is a DC, there are two converters are connected by the DC link. The combined series shunt controllers or shunt series controllers, you can say, it could be a combination of separate shunt and the series controllers as coordinated or unified. The example of this is UPFC, that is a very versatile device, and it is called Unified Power Flow Controller. Here it is called unified because the series and shunt controllers converters are connected by the DC link. If it is not by direct DC link, if you are controlling separately, then it is called coordinated. Combined series and shunt controllers injects current into the system with the shunt part and the voltage in series with the series part of the controller. When shunt and series controllers are unified, there can be a real power exchange between the shunt and the series controller via the DC link. I want to say that. For example, let's suppose here this is your line. Here we are having the shunt facts. Here we are having series. What we are doing, if we are controlling here separately by coordinated controls here, then we cannot transfer exchange power between the shunt and the series. But if we are removing this and we are having this type of arrangement, this is a fax controller series part, here your shunt, and if you are connecting by the DC line here, then there is a possibility the power will be exchanged through this DC link. And then we can control the active and reactive power independently, and the UPFC is one example of this, which is very, very versatile. It can control the bus voltage here, it can control the power flow here, P and Q independently. So all these three quantities can be controlled independently from the UPFC. Now basic fax controller, that is a shunt controller, I want to explain, because in this module only this SVC is mentioned, so I'll be discussing SVC more. And again, another advanced technology is there, that is called static synchronous compensator. Here is static wire compensator, so we normally call it SVC. Now you can see the construction of HVDC, how it is connected. This is your system here we are having. It is connected by your transformer because we are connecting at the lower voltage. Here this is your reactor. We are using anti-parallel thyristors, and these thyristors are controlled in such a fashion that the value of L can be controlled. Thereby we are controlling the impedance of this complete system. This is your fixed capacitor, this is your switched capacitors here, and they can be added so that you can say here this total effective X of the system is changed, and by that we can inject or we can absorb the reactive power. If whole this X effective is capacitive, then we can inject the reactive power, we can improve the voltage profile, we can do other purpose as well. However, if it is a totally inductive, then we can absorb the reactive power and we can reduce the voltage. So static wire compensator has been used for the reactive power compensation since mid of 1970s. It is more than 36 years old device, and till today it is more than 750 locations or SVC devices are in the system, and they are basically providing 40,000 MVAR right now. So it's so many locations in India also. Here in the there is a power grid stations of near to Bhauti in Kanpur, we are having the SVC, that's rating here is plus minus 280 MVAR. Basically we are having two devices, and that is here plus minus 140, and that is doing the purpose from very beginning, from the early of 90s. So it is from 88 and 89 onwards. So it has several advantages. Advantage that it can provide the voltage support. It will improve the transient stability. We will see later all these things. And it also damp out the power system oscillations. And we will see these three advantages by analyzing, by taking a simple example. However, another shunt device is your STATCOM, that is called static synchronous compensators or STATCOM simply. it is superior than SBC. The reason that it is here the converter based technology. If you see in the previous one, it was here your thyristor, simple anti-parallel thyristor. It is not a converter. So it is superior because we are using the converters here. The reduction in the outdoor area requirement, it requires less space. It reduces the voluminous capacitor and reactors. There are so many inductors and capacitors were used. Here we require only one capacitor or inductor that will solve your purpose. So that's why we require the less space as well. Here its performance is better in the low voltage system. There's in earlier cases the thyristors, once you are firing, if you are changing the inductance, what will happen? You are just delaying the firing angle or you are advancing the firing angle. Thereby we are generating the harmonics in the system. Here, however, it reduced the harmonics very well, and therefore there is no need of the filters. Those can be filtered out. So the dynamic performance also and the stability limit enhancement with the STATCOM is better. Now the question here, why the voltage performance is better for the STATCOM compared to SBC? To understand this, in the previous case here, you saw here the reactive power provided by this whole system, this Q, it is nothing but V square upon that the X effective. Voltage here is the voltage of the system. Here this is V. If voltage falls, what happens? This Q generated is less. Again, let us take a new page. Here in SBC, I can say let us take SBC example. Here I am talking about STATCOM, and then we will see the difference for the reactive power support under the low voltage. So the reactive power provided by your SBC, it is the V square divided by your whatever can say XC or X effective which I am using. Now you can see if your voltage falls down from 1 per unit to let's suppose 0.8 per unit. When it was 1 per unit, it was giving the reactive power at 1 per unit, it is 1 over X effective. Now at this value, this X Q will be your 0.8 square divided by X effective, and it is 0.64 upon X effective. What does it mean? Now the reactive power provided when the voltage is less, the reactive power provided by this system is less. It means that when we need more reactive power, it is providing less. Here it is providing more, it is 1 per unit. So therefore here you can say the reactive power reduction is the square term, and therefore when we need more, it provides less. So this is not so superior. Now come to your STATCOM. In STATCOM what we are doing? You can see in STATCOM here we are just injecting the current. This is your voltage. So the reactive power here, this Q, will be nothing but your V into I, and we can fix the current limit. The limiting value here is your I. So let's suppose it is at the limiting heating value and your voltage is reduced. So earlier it was 1 per unit, so your Q was I, and now once it is a voltage is 0.8, now Q here is 0.8 I. Now this is also reducing, no doubt, but what happens earlier in SBC, it was your Q SBC was 0.64 times of your Q original. So it was more reduction than this, it is 0.8 times of the original value. I can say 0.8 Q naught, and here 0.64. So this is giving more reactive power when you require compared to SBC, although this is also reducing. So that's why it is said the improved performance at here low voltage. Another here that your reduced need of filters, as I said, the requirement of filters are minimized because here we can use the pulse width modulated converters firing circuit. By that we can eliminate the harmonics generated by these converters, and even though sometimes we can improve the power factor of this very effectively compared to your SVC. So SVC is nothing but a variable impedance source, variable impedance device. However, this STATCOM is your variable voltage source. This is the difference between the STATCOM. So SVC is your variable X, that is a shunt. Here it is your variable voltage, and then we can change the voltage and thereby we can change the current. So here if this is your voltage VSH, so I can write V minus VSH divided by the transformer impedance is your I. So this is your, I want to say this is a voltage source device, this is your variable impedance device. So here we can generate this voltage source with the fundamental frequency, so there will be no harmonics. So the reduced need of the filters. Wherever there we require some filter. But another advantage of that SVC here, if you are putting the filters here at the fundamental frequency, those filters here they are used, they provide the reactive power at the fundamental component. So there's this filters sometimes very advantageous that they will inject the reactive power at the fundamental. However, for harmonic frequency they will work as a filter and it will be going to the ground. So this, but again the cost will be more. You are putting another extra device. And the dynamic performance, it is better, and enhancement of stability will be also better, and then only we can understand this part only based on if we go for the characteristic of these devices. And then we are just before that again we have to go for the basic fundamental about the stability, that how it is going to improve, and then we will see that this STATCOM is better than SVC. But the SVC is the oldest device in the FACTS family, and that's why still it is cheap also. This device is very expensive. The main disadvantage of this one is here it is expensive because here we are using converters. So many thyristors are used wherever we are using 2 thyristors. So that device is cheaper, this device is expensive. Now another difference here, the 2 type of STATCOMs are available, that is a voltage source and the current source. As I said, the CSC or current source you have to use the inductor. Here we have used inductor, so this is your CSC. Here you are using capacitor, it is your voltage source converter. Now these STATCOMs are now people are planning to put in the distribution side. Earlier people are using simple capacitors. Now with the help of that we can improve the static as well as the dynamic performance of the system, because now the cost of these devices keep on going down and we can enhance the power system dynamics, or you can say performance, both static as well as dynamic with the help of these compensator, and that is a shunt controller. So let us see the comparison of STATCOM and SVC. Whatever I told in the nutshell, now we can go in the detail. Here I have written the STATCOM, here it is your SVC. First we will see the comparison, that this STATCOM acts as a voltage source behind the reactance. As I said, it is your voltage source. Here it is just acting like a variable susceptance or impedance. The STATCOM is insensitive to the transmission system harmonics because we are injecting the voltage source, and that voltage source is independent of the system harmonics. However, this is very much sensitive to the system harmonics, and that there may be some resonance because we are using some parallel capacitor and inductors, and that maybe some other harmonics component may resonate, and this may give you outage or you can say damage of that equipment and the other elements of that SVC. STATCOM is having higher dynamic range. Again, this comparison I will come later, but you should know here right now, this here it has the larger dynamic range, means it can operating range is very wide compared to your this SVC, which is having a smaller dynamic range. Of course, this STATCOM generates less harmonics, fewer harmonics. However, it generates more harmonics compared to the STATCOM. The STATCOM has faster response within milliseconds and better performance during transient. Its performance, that is SVC performance, is slow during the transient. STATCOM, both inductive or capacitive regions of the operations are possible. Here you can operate both the region, that is the inductive as well as the capacitive. SVC are mostly operating in the capacitive region. Means whatever just you are connecting here, your this thyristors, and here your inductors, here you are using capacitors variable. So total here normally your X effective will be your Xc, means we are using in the capacitive region most of the time. The one STATCOM that is we are having in the power grid substation Bhautik Kanpur, it is operating your Xc mode always. STATCOM can maintain a stable voltage even with a very weak AC system. Means your system is weak, it can maintain the voltage compared to your AC weak system. As I said, the reactive power generation, here the Q is, once voltage keep on down, then reactive power generation is also reducing, but at that time we need more. Here that reduction is less, so it is better, it can maintain the voltage stably with even though very weak AC system. STATCOM can be used for the small amount of energy storage device. As I said, here we can use the STATCOM for storing some energy because we are using the capacitors here. As I see here, this capacitor or this inductors, they can store the energy for little amount. No doubt this is not huge amount. If you are going for the huge storage, then cost will be very, very high. But that energy can be given during the emergency condition, and then it will be better when you need some power in the emergency condition, and it can provide. So it can handle a small amount of energy as well, but here there is no scope of storing the energy. The temporary overload capacity translate into the improved voltage stability. Here we can go for the temporary overload capacity, and therefore we can again improve the voltage stability of the system, whereas in SVC it is not possible. So in this lecture, just we saw that the importance of the FACTS controller. We also just compare your STATCOM and your SVC's devices, and we saw that STATCOM is better than SVC. But the main problem with the STATCOM, it is expensive than SVC, and due to that, here the SVCs are very, very popular, and it is already located in the more than 750 locations all over the world, and it is feeding 40,000, almost more than that, MVR power to the system. So the SVCs are very popular, and then here now I am going to just these two I'll show you later that how they are, who is better. Again, based on that I mentioned here, we will compare in the next lecture. Thank you.